Welcome to the Stirling Engine Anonymous meeting. I mean episode 2 of the Stirling Engine Design Project. If you missed episode 1, click up there somewhere for a link to episode 1, which will explain and establish a context for this video. Now, in this video, we're going to look at how I can develop a dynamometer that will allow me to test and analyze the performance of this engine really quickly and efficiently, so I can focus my mental energy on design changes in the engine and refining and making it really amazing, rather than spending all this time, watching numbers on meters, writing numbers down, or typing them into a spreadsheet. I want a tool that is just really quick and easy, where I fire up the engine, click a button, and it will just run through the whole performance curve of the engine and give me a nice graph in a really quick and easy way. So that's what we're focusing on in this video. So the response to the first video I made has been really phenomenal. I'm super excited about the response from the community of Stirling engine enthusiasts. And in the intervening time, a number of really interesting, smart people have reached out to me that shared my passion for this project and have given me a lot of really interesting input, ideas, guidance, and pointers that will help me as I journey forward with this. To measure the mechanical power output of an engine, you've got to do three things. You've got to measure the speed in RPMs, you've got to be able to measure the torque output, and you've got to do this while applying a variable load that puts the engine through its paces so you can create that beautiful power curve. Here's the block diagram for my proposed dyno concept. The engine gets bolted into the test stand with a nice aluminum flywheel on it. The aluminum flywheel will interact with a disc that has magnets on it, creating eddy currents in the aluminum. The engine power will be dissipated in the aluminum flywheel. It's going to get slightly warm. The torque produced will be measured by a torque transducer, which outputs an analog signal proportional to the torque. An A to D converter will then digitize that signal and send it to the microcontroller. This whole assembly is mounted on a moving linear stage that's driven by a stepping motor. The microcontroller can then change the distance between the magnets and the eddy current disc under computer control. This will provide a variable torque load to the engine. An eddy current brake is not terribly good at producing torque at very low RPM. It needs a moving magnetic field to work. So one workaround for low speed torque will be to put felt pads on the magnet plate that will physically rub against the flywheel, creating drag at lower RPMs. This is just an optional idea, but I have it at the ready for solving that problem. The unit will have a text display and some push buttons so it can be operated manually, but the primary mode will be to send serial data directly to a program like LabVIEW or Microsoft Excel via a serial port. One of the key salient features to this design is that there are no shaft couplings, additional bearings or belts or anything like that that applies any kind of parasitic load to the engine. Absolutely all of the engine's mechanical power is absorbed by the brake and is measured by the torque transducer. Another important feature is that I'll have the linear slide completely back away from the engine for easy starting. So there's plenty of room to get your hands in there to twiddle with the flywheel and get that motor started. As soon as the engine is running, the stepper motor will move the rig back into position and start applying the load. A tiny magnet embedded in one of the gears induces a small voltage in a 3.3 mH surface mount inductor as it spins. This is converted into a TTL pulse by a simple circuit. This setup is very tolerant of misalignment, vibration, dirt contamination, very reliable. The heart of this contraption is the torque transducer. I started shopping around for one and was quickly smacked upside the head by the high prices of these devices. And I get it. You don't sell very many of these and they're precision, so they're going to be really expensive. So in my usual crazy style, I thought, hey, why don't I just design my own? So that's exactly what I did. Now most of these torque transducers are based on strain gauges. And I don't know much about strain gauges, nor do I have any lying around. But what I do have lying around is lots of wire, magnets, and bearings and stuff like that. So I decided I'd try to build an electro-dynamic torque transducer. So what is an electro-dynamic torque transducer? Think of it this way. If you have a device that can convert current to a torque, and that's exactly what a motor is, if you take that motor and you put a position sensor on the shaft, connect that position sensor to a closed-loop servo controller that tries to hold that shaft still. Now imagine that this shaft is sitting still and you try to put a torque into that shaft. The motor is going to fight back with an equal and opposite force, and the current that's creating that force will be exactly proportional to the torque, provided of course that the motor has a linear transfer function. The electronics for this thing is a little bit complicated, but the mechanics are so bone simple I knew I could pull it off. Now you could probably get this thing to work using just an off-the-shelf brushless motor as the actuator. But there's two basic problems with that. Those motors are designed for power output, not instrumentation. So their air gaps are really tiny, and potentially you'd have non-linearity due to the core saturation at some point. And there's also a lot of residual cogging torque, which would also affect your linearity. By building your own motor with air core coils, you can have extremely high linearity because the air gaps are huge and there's no iron directly in those cores that's ever going to get anywhere near saturation. It becomes a very precise torque to current and current to torque transducer. And since this motor doesn't actually rotate, it just moves a few degrees back and forth, you can make it into a long, skinny, stretched out thing where each coil actuator has the most leverage over the center axis as possible because it's farther away. This allows you to get quite a bit of torque out of a fairly wimpy electromagnetic actuator. To get this closed-loop servo concept to work, you need a position sensor that can output an analog voltage that's proportional to the angle of the rotor. The electronics can then take this position signal and subtract it from a reference voltage. The result is what we call the error voltage. The polarity and magnitude of this voltage tells the electronics which direction and how hard to push on the coils to get the rotor to return to the zero or null position in the center. Since there's so many magnets in this whole thing, I thought it prudent to go with what I call cross-domain sensing. I use an optical sensor because it's not going to be interfered with by any of the magnetism that's flying around this contraption. A small metal vane attached to the rotor of the actuator interrupts the beam between an emitter and a detector. This is the typical configuration for what they call an optical slotted switch. But in our case, we're not looking for switching action. We're looking for a linear proportional response to the angle. So this is where we had to do some thinking. The typical configuration of a point source LED and a detector creates a very sharp knife-edge transition zone. It casts a very sharp shadow over the sensor, and it turns on and off rapidly as the flag moves. What we need is an optical detector that has a very large area, so that the shadow, as it crosses the device, will be proportional in strength rather than a sharp cutoff. I looked around in my parts bin for such a large area detector and found none. But then I remembered that you could use an LED both as a light emitter and as a light sensor. And if I used a diffuse LED, that would effectively spread out the detection point because it's no longer a point source. So now it was time for some tests and experiments. I have a ton of RGB surface mount LEDs in my parts bin, so I tried a pair of these and tested to see which channel gave the highest output signal, and definitely the red works the best. So I used a pair of the red LEDs and configured them face to face and attempted to measure and plot their response as an analog sensor. The first test was kind of disappointing, but then I realized if I take a little piece of plastic cup from a milk bottle that acts as a diffuser and glue that over the detector, I can actually increase the range and linearity substantially. The response isn't totally linear, but that's not necessary here. The only impact this nonlinearity has is potentially on the stability of the servo loop. It has zero impact on the overall accuracy of our torque transducer. I realized that if I mounted the sensor closer to the axle, I could then dilute the motion of the whole rotor assembly and use a smaller, more linear portion in the middle of the sensor's range. The only problem left to solve is how to make this temperature stable. LEDs are not very temperature stable as far as their sensitivity to light and their output of light. If I just use this setup as is, the null position would drift around with temperature, and that could conceivably mess up my linearity. So I had to figure out a workaround for that. I solved this problem by using two pairs of LEDs. One pair is the sensor, and the other one is a compensator. The compensator is just the two LEDs glued together face to face and set up in a circuit that adjusts the LED current of both of the emitters simultaneously while monitoring the output of the compensator LED to maintain a constant output. This effectively removes the temperature sensitivity because the two pairs should track each other very well as long as they're nearly the same temperature. I 3D printed some coil forms and then made a little simple mold out of two aluminum plates coated with wax paper. This prevents the epoxy from sticking to the aluminum so you can get the thing apart and remove the coil after you're done. Once the coil is finally wound, it's time to slip in the coil mounting fin. This part just slides in and smushes up against the epoxy. I try to clean it up nicely so that when you separate it, you don't have to do too much trimming of epoxy.
And countless other business, cultural, and leaders, society, to schedule local countries, and looking tons of action. Today in posting bad news.
The final version of the position sensor had to be both mechanically robust and stiff, and also shielded from both ambient light and external electrostatic fields. So I basically made a little brass cage for the thing with a slot in it. The pot allows you to adjust the center null position to exactly 2.5 volts right in the middle. Now I want to say a few words now about testing. Now, I'm a huge fan of doing really sketchy, quick and dirty tests up front as soon as possible. These little tests, even if they're inaccurate, sloppy, messy, they give you the touch and the feel and the understanding of what the real problem is. So even if at the end of your sketchy test you realize that you have to do it again, what you learn during that sketchy test helps you design the experiment for the second round. It helps you confirm your assumptions and not waste time doing stuff that is totally unnecessary or inappropriate. Now, if you do a sketchy test, often it's going to be good enough. A lot of these things are just a rough order of magnitude. And if you want to maintain a really high level of productivity, you've got to be super stingy about your time. Do the absolute minimum first and check to see if that's good enough, because often it is. Since the magnetic actuators were a total DIY roll-your-own job, I really had to do a lot of tests to confirm that I understood exactly how it really worked and to get good numbers on what the performance is. My super sketchy quick and dirty test of the eddy current brake proved that it could easily dissipate 11 watts using my power drill. If my little engine can put out 11 watts, I'll eat my shoes. Well, I'm super pleased with my home-brew electro-dynamic torque transducer. This thing ended up costing about $100. I didn't have to wait for anything to come. I had pretty much everything I needed on hand. So now that this part of it is finished and working, the next steps are to start building the actual dynamometer. So stay tuned for episode 3. So once again, thanks so much for watching. Hope you enjoyed and learned. Please like, subscribe, comment, help me grow my channel. I want to make more great content like this. Thank you very much.